Hi, my name is Mike Holt, and this is the second DVD of understanding grounding versus bonding as it relates to the National Electrical Code. Now, I can always reinforce this is what you have to have. Make sure you have a 2014 NEC. Make sure you have the grounding and bonding textbook. Lay it all out. If you're watching as a DVD, put it on pause whenever you want to. If it's live stream, not live streaming, but if it's going to be on the internet, you put it on pause. As we discuss things and we move things forward, be part of the process. Don't just sit there and watch this. Make sure you get yourself engaged. But before I get started, I just want to take a moment to dedicate the work that I do and the efforts that I make to God for giving me the opportunity and the skills to help others. I'm going to just quickly introduce our video team members that's helped us. And I just want to thank you guys. People that are watching this live or people watching the DVD, they have no clue how much effort all evenings. After we get done, you guys are working late. And Ryan, especially, you find out all those little tiny details. And man, these guys
I don't know
work.
whether to say thank you or not.
Yeah, that's perfect,
Thank
man.
you, I think.
These guys are tireless. You understand, at nighttime, we're working and we're looking at every graphic, every tech. We're testing each other at breakfast and lunchtime. We're making sure we're doing good. And so I'm just going to start on the left-hand side, and the introduction was already done in the first DVD. Mike Pillarella, Massachusetts area. Thank you so much. Eric Stromberg from New Mexico now.
New Mexico.
Okay, Ryan Jackson from Utah. Scott Harding from Washington, D.C. area, or Maryland and Virginia, somewhere in there. And then Dennis Carlton from Colorado. So, again, guys, I really, really, really appreciate what you guys are doing for us and helping the team there. All right, let's talk about the program. Again, just to review it, the scope of this program is limited to solidly grounded systems that are operating in 120, 12240, 12208, 277 480, and sometimes people get into 347 600 volts. So all our comments are focusing on that unless we talk about an ungrounded system or we get into a corner grounded system or a high resistor grounded system. We're not talking about utility distribution systems. We're not talking about static electricity. We're not talking about lightning protection, NFPA 780. We're focusing only on NFPA 70, the National Electric Code. And on the first DVD Article 90, Section 90.1, what's the purpose? The purpose is to make sure we safeguard persons and properties by the use of electricity, and the NEC is an installation standard. So when we install the product, it must make sure that it's going to practically protect people. Nothing is perfect, but we're doing the best we possibly can. Moving off of that, I'm going to Part 7, Methods of Equipment Grounding. 25134, Grounding of Fixed Equipment. The only rule I want to cover here is that you have to be sure that all the circuit conductors are contained within the same raceway. And the purpose of that is to ensure a low impedance fault return path. Remember we talked about this yesterday, the GEMI program from the University of Georgia Technology Institute. Well, they've shown if you put the equipment grounding conductor inside of a raceway, metallic or non-metallic, if it's metallic, of course, then the metal raceway carries most of the current. If you put it inside a non-metallic raceway, then the fault current would be higher because it's a lower impedance path than if you put the equipment grounding conductor and you separate it away from those circuit conductors. And we're always trying to get the lowest possible fault return path, which means all circuit conductors, including the equipment grounding conductor, must be contained within the same raceway. Let's go to the next rule. 25140, grounding of ranges, ovens, and dryers. You need to have a 4-wire receptacle now for ranges, dryers, and ovens if it's going to be of the receptacle type. This is a violation. We used to use 3-wire with the neutral bonded to the enclosure. This is a violation for a new installation, but it's not a violation for an existing installation. So here's the existing installation. That would be okay. They have the neutral bonded to the enclosure, neutral connected to the neutral terminal here, and then the appliance itself. One thing you got to be careful of, electricians, appliance people, this concerns me. The ranges and dryers and ovens have the neutral bonded to the frame, assuming it's going into an existing home that had a 3-wire receptacle. So if a person's not aware of this, then they might hook this up with a 4-wire cord and have this thing improperly connected, plugging into the receptacle. And I've actually seen instructions from a Kenmore dryer where they actually took the hot wire in the instructions and connected to the frame of the dryer. And I have those instructions. And I sent it to the Consumer Product Safety Commission. And Sears said, well, if the customer has any problems with the dryer in a range, then they should contact us. And this was about 6 months ago. So if anybody knows anybody, the Consumer Product Safety Commission, maybe you guys know somebody there. And I know they're in Washington, D.C., and I forgot the name of the guy that was there. There is actual instructions from a dryer to connect the phase conductor to the case of the dryer. Wow. Now, one of the guys sent this to me. He contacted them, meaning the hotline for Sears service, and the guy said, no, it's fine the way it is. So we are what, November the 2nd, 2013? And I have not, it's been, 6 months from the Consumer Product Safety Commission has even responded at all. So you really need to be careful. You can't even just take a dryer and read the instructions and hook it up without being qualified. So you got to be very careful there.
Wow.
If anybody wants that, you let me know. I'll be glad to send you the PDF that I have on that information. Okay, I'll send it to you guys.
Well, we got to get it to UL as well.
Okay, anybody, streamers, you guys that are streamer guys, let me get this because I'm like, what can I possibly do?
Yeah, people
you got to kill somebody here. So I'll get it. And streamers, get with these guys, and I'll get you that information. All right, 251.46, connecting a receptacle grounding terminal to a metal box. The code says the grounding contact of a receptacle must be connected, if it's in a metal box, to the actual metal box itself. Now, the metal box is going to have to be what? Connected to an equipment grounding conductor of the wire type or metal raceway, whatever it's going to be. Orientation. Is the ground up? Is the ground down? Is the ground left and right? It doesn't matter. Receptacles installed in surface-mounted boxes. If you put a receptacle in a surface-mounted box, then you do not need to put an equipment bonding jumper from the grounding contact of receptacle to the box, as long as you remove one of the insulating washers that holds the screws so that the metal mounting yoke is in direct contact with the box. And, of course, the box is connected to an equipment grounding conductor, and then we're fine. So you remove one washer, you're good. Whether it be a bell box or, a weatherproof box, whatever it is, it's a surface mount. This only applies to surface-mounted box when there's direct metal contact between the yoke and the mounting surface of the box or the ring that's used.
It's becoming less common, and a lot of people don't remember this or don't want to hear it, but you look at that graphic, and on the far left, you mentioned the box is connected to an equipment grounding conductor. Some people might be looking at this and saying, well, I sure don't see a green wire. Remember, EMT is an equipment grounding conductor. We say equipment grounding conductor, that includes EMT.
You know what I think right here? I'm going to have Mike put it here. EGC.
Yeah. Mm-hmm. That's not bad idea.
EGC.
But people forget that,
Yeah, nice.
EGC. It wouldn't be many places, but there might be a couple places to remind people, there's your equipment grounding conductor.
Right.
Mm-hmm. We're good to go there.
And you could even put an EGC on the little screw, 632 screw.
Okay. If you put a receptacle on a cover, the code requires that there be an equipment bonding jumper from the grounding contacts of that receptacle to the box. So in this example here on the right-hand side, I would have to have an equipment bonding jumper from that receptacle to the box. However, if you put a receptacle on the cover, a bonding jumper is not required from that receptacle to the box if the receptacle is secured to the cover with two fasteners that have a screw locking means and a non-flat area for attachment to the box. Look at this photo here. If I have a cover that has crushed corners, and it's a flat area here, and I use this screw with these fasteners, then I do not have to have an equipment bonding jumper. Here's the crushed corners. You take a receptacle and you secure it to the cover with two fasteners that have a screw locking means and a non-flat area for attachment to the box. So these two screws are used to secure the receptacle to the cover. Then you have this flat crushed area that makes contact between the cover and this box, and then you screw it in there, and now we've made the bonding. And that takes care of that. Self-grounding receptacles, 250.146b. Well, if you have a metal box, and the box is connected to an equipment grounding conductor, if you use a self-grounding receptacle, that's what it looks like right there, where the screw is connected to the receptacle, then simply installing that receptacle into a box or a ring accomplishes the bonding of that grounding contact of that receptacle to the box via the screws themselves. Nothing else needs to be done. I mean, I would only use self-grounding receptacles as an electrical contractor. I wouldn't mess around with a bonding jumper to a receptacle. Isolated ground receptacles. An isolated ground receptacle means that the mounting yoke of that receptacle is insulated from the grounding contacts of that receptacle. If you took a continuity tester between this grounding contact and the yoke, you'd measure infinity, where if you'd gone to a regular receptacle, if you measured a continuity between the grounding contact and the receptacle to the yoke, you'd measure 0. Okay, so now the mounting yoke is not connected to the equipment grounding conductor. So an isolated ground receptacle can be installed. And you do not have to connect that equipment grounding conductor, and that's where you get your green wire with yellow stripes. Not required, but if you wanted to use green wire with yellow stripe, then that's traditionally the practice on isolated ground receptacles. Careful with isolated ground receptacles, because here's the MC cable of traditional type. I mean, this is armor cable. Is the outer sheath of armor cable listed as an equipment grounding conductor?
Yes.
Yes. So therefore, this connector, proper fitting, installed in this box, which means this box is the equipment grounding conductor. Here's an isolated ground receptacle. When you put the metal mounting yoke, that takes care of ensuring that the mounting yoke is connected to an equipment grounding conductor. Then you bring an equipment grounding conductor to the isolated ground receptacles. That means the grounding contacts of that receptacle is connected to an equipment grounding conductor. Scott.
And I was just going to say that AC cable with the equipment grounding conductor is usually referred to as HFC, or hospital facilities care, or healthcare facilities cable.
Yeah. It's usually ACHC, right?
Yeah.
Armor cable, health care.
Right.
Yeah. Now, here's traditional MC cable, which has an insulated equipment grounding conductor of the wire type. Well, yes, that takes care of the grounding contacts of that receptacle, but it does not ground the metal mounting yoke of the box. As a matter of fact, this box is not connected to an equipment grounding conductor.
Nor is the cable sheath.
Neither in the cable sheath. So we have a serious problem here. Now, this is Interlock MC all-purpose cable, and this cable itself is going to be listed as an equipment grounding conductor, which means a box connected to the equipment grounding conductor, and it has an insulated equipment grounding conductor connected to the isolated ground receptacle, and that's okay. If you want to use traditional MC cable where the armor cable is not listed as an equipment grounding conductor, and bring an equipment grounding conductor to wire type and connect it to the box, and then bring another equipment grounding conductor that's, say, insulated, maybe green with a yellow stripe, connected to the receptacle, that's okay. Let me make a quick comment about isolated ground receptacles. Let's take a look at this slide right now. This is from the IEEE 1100, which is the Emerald Book. The results, meaning the performance of isolated ground receptacles. The results range from no observable effect, the desired effect, or worse noise conditionings than when standard grounding configurations are used to serve electronic load equipment. Isolated ground receptacles is a joke. It is ridiculous. I'm sure there might be an application somewhere where we have an isolated ground system with the feeders, the insulated conductors, and the whole thing. Maybe sound recording studios, maybe TV recording studios. There might be an application here or there. But when you see equipment saying connect us to an isolated ground receptacle, the electrician's just going to put an isolated ground receptacle. He's going to run not MC cable. Right? He better not run MC cable, right? Because we have a problem there, but he probably is going to run MC cable. He'll run MC cable, connect it to the box, and go right to the isolated ground receptacle, and then go back to the panel, put it in the grounding terminal of the panel. Nothing was accomplished, but everybody feels better about that. Ryan.
Well, and the ramifications get worse than that. I mean, I've done jobs as an inspector. You plug in your tester, it's not connected to anything. Well, it says isolated ground, and it's as isolated gets, right? There's nothing on that screw. I mean, these things freak me out, man. I don't like these things at all. People misunderstand what it is, and they think it's solving the world and keeping it safe from communism, and it's not doing anything.
You know what?
And it's dangerous.
And you're right, and I totally forgot about that. I mean, I know the history of the 80s and the whole. I forgot that some people think an isolated ground receptacle is not supposed to connect it to the building ground. Right. It's an isolated ground. You go outside to this counterpost ground. You put 3 10-foot ground rods 10 feet apart in a triangle. Like, what the heck is going on here? And
Exactly.
this is reality. This is what they did in the 80s, right, guys?
Yeah.
And
Yep.
so there must be some people still around thinking that we need to make sure that we ground this isolated. I forgot that people might be doing it today.
Oh, yeah.
Yeah.
You don't want an isolated ground receptacle, but if you put an isolated ground receptacle, you connect the grounding contacts of receptacle to the box, and then you connect it to the panel, and then everybody's happy, and who cares? But you don't make it isolated. 250-148, attaching equipment grounding conductors to a box. Okay, the continuity and attachment of equipment grounding conductors to metal boxes. Where circuit conductors are not spliced or they are not terminated in a box, then the equipment grounding conductors can pass through the box without terminating to the box. And here's this example right here. So these conductors are passing through the box. They do not need to terminate to the metal box. Where circuit conductors are spliced or they are terminated on equipment in the box, then equipment grounding conductors must terminate to the box. So here is an equipment grounding conductor. What do we got here? Okay, here's equipment grounding conductor. The circuit conductors are spliced, so therefore the equipment grounding conductor is going to have to terminate to the box. If this was non-metallic raceways going to a metal enclosure, then 250.86 would require us to make sure that enclosure is connected to an equipment grounding conductor. Separate rule. 250.148A, splices for equipment grounding conductors must be made with a splicing device identified for the purpose. So, red wire nuts, they're identified for the purpose, they're fine. A green wire nut is identified for the purpose, that is fine. Just a note that green wire nuts could not be used. It's not a violation of this rule. This would be a violation of 110.3b, that this equipment is not being used in accordance with listing and labeling instructions, and it's not listed for the use as a circuit conductor. Continuity of the equipment grounding conductors. Here's your equipment grounding conductors right here. Equipment grounding conductors must be pigtailed so that the removal of a device or luminaire won't interrupt the effective ground fault current path. So equipment grounding conductors have to be all pigtailed. This is a traditional MC cable, so we have to get to the box, and then we have a pigtail going over to the receptacle, and then of course if you pull that receptacle out, you're not going to open up the equipment grounding conductors on the downstream portion. 250-148C, equipment grounding conductors must be connected to the metal box by a grounding screw that's not used for any other purpose or a listed grounding device. So here's your grounding screw. That'd be a 1032 screw threaded into that box with 2 threads engaged. That screw is not required to be green. The listed grounding fitting would be like a ground clip. I never really was fond about these things. I don't really like this, but the code does recognize that as it means. And I think those are probably, I don't know, the listing might even require those to be green because it seemed to me like they seem to be a greenish color. I can't remember about that.
Screws.
Yeah. Termination of equipment grounding conductors in a metal box. Equipment grounding conductors must be connected to a metal box by a screw or fitting that's not used for any other purpose. When we first started doing Romex, we always put that Romex right around that screw, and then this should look like it's machine screws right here, and it probably should wrap around the other direction, so as you tighten up the screw, it maybe would tighten up. Well, it's actually going to be pressed inside there. So that's a violation either way. And looks like a sheet metal screw. That's a violation.
Yeah.
Part 8 of DC systems. I'm not going to really get much into DC systems on 250.166 other than to state that DC systems used to say on 250.166 that the sizing of the grounding electroconductor for a DC system would be sized based upon the size of the phase conductors of the DC system. So you could have huge phase conductors and you can have a grounding electroconductor that might be 500,000s or multiple parallel sets of 500,000s when it made no sense because the AC system, the largest grounding electroconductor is 3/0, then why would the DC system have this much larger grounding electroconductor when they're both performing the same function? So the 2014 code just simply said that 250.166 tells you what to do, but in no case is the grounding electroconductor for DC system required to be larger than 3/0. Okay, I'm done with with chapter 2. I know we have some internet streaming because we're transmitting this video live on the internet as we do all our recordings now. And we've had a bunch of guys helping us out here and also posting some questions. So, Ryan, do we have any questions that we want to just kind of field here that we can hit?
Yeah, just a couple. One is regarding the inter-system bonding terminal, and that was 250.94. And Don writes, it seems the intent of that rule is to provide the inter-system bonding terminal on the exterior of the building so the phone and satellite guys can get to it. But the code doesn't really say that. It just says it has to be near the service equipment, which, of course, especially in a commercial building, that might be dead center of inside of a building that's quite large and significantly far from any exterior point.
It's a great point, Don. And I have some problems. I like the concept in theory of bonding termination because in my house that I built, I did not have the grounding electric conductor exposed. I had no inter-system bonding termination. When the cable guy came out there, he did not ground the cable. And the result is I destroyed lots of equipment, not recognizing I did not provide any spot for the cable guy. My new house, I have clearly an inter-system bonding termination, which makes it easy, and it's outside, which works great. But I just built an accessory barn. Some of you guys have been in my house. I have nothing there. It's just simply, and I run a feeder out there, and I just got a barn out there. And now, guess what I have to do? I have to put an inter-system bonding termination to a building doesn't even have any communication system at all. That is nuts. And if I have a service inside of a building, which is not outside the building, I got to put it inside the building, but the communication system's outside. But I have a basement. In other words, there's no way that we can write, not we, because I have nothing to do with it. There's no way a rule is going to be written that's going to be perfect to get it where you need it to be. So the code does not say inside or outside, but that's where our job is to try to understand what is the best need for the customer, where do we want to put this so it can become effective, and that would be probably outside, but maybe where the systems are coming together, and it might be inside of an equipment room. So where is it the best place?
Okay, and then the other question is, what's the use of grounding enhancers or conductive cements for grounding purposes, and saying that it's sometimes used in South American countries?
Okay, actually used in the United States at times. Sometimes they'll use, I think, bentonite, I think is a term that's used. And what they'll do is they'll actually core hole about a 12-inch diameter, and they'll put this bentonite in there, and they'll put like a ground rod in the center of that. What that has done is the bentonite, it actually created the surface area to be a 12-inch diameter rod. So now your contact resistance, remember we talked about you put a ground rod in the earth and 1/10 of 1 foot is 25%, and then you went 6 inches away and it came out to be 52%, and you went 1 foot away and was 86% of the resistance, or 68% of the resistance. Well, when you put a ground rod in the center of this 12-inch diameter bentonite, which is a conductor, the amount of surface area that you have is a 12-inch ground rod. Now, it's not a conductor in its sense, but look how many parallel paths that you have. So the ground resistance, let me phrase that, the contact resistance now of that ground rod relative to the earth is much lower than it would have been if you just put a ground rod in the earth. And that's the reason why they do that. Now, why do they want to get it so low? I have no clue. That makes no sense at all to me. That's just somebody's thinking, well, it needs to be low. Why? I don't know. Not within the scope of what this program is about.
That's really interesting because one of my hobbies is making wine, and you use bentonite when you make wine. You actually make it into a slurry. It's got either a negative or a positive electrical charge, but very strong, and it sucks. Oh, if you have solids in your wine, you pour it in there, and it sucks all the positively charged junk out of your wine, and then you can get rid of it all. So it has a strong electrical charge, the bentonite does. So that's interesting. I'd never heard that's what that was.
Does it make sense, though, we're making a big electrode?
Yeah, oh yeah,
surface
absolutely.
area?
And it would work because you can see it when you make wine. That's interesting.
So one of the reasons for having a low impedance might be to get drunk, but that's another issue.
Right, no, absolutely.
No, one reason to use a bentonite is to get drunk.
Yeah, I'm not going to let anything impede me in that endeavor. It just popped up.
Okay.
What is a ground grid? It shows up in the California test, some sort of a test. So,
there is nothing in the electrical code as it relates to a ground grid. Agricultural buildings and swimming pools have equal potential planes, equal potential grids, but there's no such thing as a ground grid in the electrical code. Substations, NFPA, I'm sorry,
IEC.
What is that?
Standard 80, IEC 80.
International
Substations.
No, a
power
substation
plants.
would be, no, substation is
Electrical safety
IEEE
code.
standard 80,
Right.
deals
National
with the
Electric
grounding
Safety
of
Code.
substations. So that's high voltage
NESC.
systems.
Yeah.
We have no ground grids.
But then you're going to see them in power plants and wastewater
Again,
treatment
that's not
plants and-
electrical code.
Right.
That's not substations.
Yeah, there was a proposal submitted for 2014 to actually have a design for a ground grid and have it be included as an electrode. It did not make it through. It was rejected because it was hard to get it together. So it may
don't
be there one day,
need
but it's
any
not
more
there now. It's too
grounding.
hard to
Just-
define
Yeah.
it.
We don't, just 2 ground rods and move on. I
Right.
mean,
It was too
all right,
hard
we're
to
done.
define.
I'm done. Finished. Chapter 3. Wiring methods. Article 300, wiring methods. For some reason, those 2 don't make sense to me, but I'm going on. 300.3, conductors. We talked about this before. Another rule telling us what? Circuit conductors must be grouped with the phase conductors. We talked about that because of the low impedance path that we want to maintain for that effective ground fault current path. Grouping would also apply to parallel. You parallel multiple raceways, you have to bring an equipment grounding conductor in each of the raceways, and 250.122F1 tells us how to size the equipment grounding conductor for each of those raceways, which is based upon the rating of the overcurrent device. 300.314, outlet, pull, and junction boxes and hand-hold enclosures. So you have all these different outlet boxes, different possible junction box, handhold, condo bodies. That's what 314 is about. Non-metallic boxes. If you have a non-metallic box and you have metal raceways, then the code allows you to use that application as long as you take an internal bonding means between all the raceways. So put a bonding bushing on each of those raceways. And that's your example you had earlier, Ryan. Put a bonding bushing and a bonding jumper timed together. Now you can use a non-metallic box with a metal raceway. Ryan, did you want to say something about the rule?
Yeah, I actually kind of thought this was obscure, but evidently everybody else says, yeah, I've seen this. And where I see it actually is sometimes in residential. People will buy just plastic, outlet boxes for switches and receptacles, and then for whatever reason, they'll want to run MC cable. So they'll run MC cable into a plastic outlet box, and then, of course, there's no way to connect that cable armor to an effective ground fault current path, and that's another example of a violation of this rule that I've seen.
Okay, let's take a look at the actual rule because I was working with the exception in my graphic here.
Right.
Okay? But the rule that you're saying is non-metallic boxes shall be permitted only with open wiring on insulators, concealed knob and tube wiring, and cable wiring methods with entirely non-metallic sheath, cords, and non-metallic raceways. And you're saying you've actually seen somebody use an armored cable or MC cable with a non-metallic box.
Right.
And this exception, number 2, really doesn't even make kind of sense in the context of the rule because the rule is saying, oh, we're going to accept that conversation, what we're talking about. Well, I use a non-metallic box, but with metal raceways, not metal cables, that way you can bond them together.
I actually saw once out on a construction site a plastic panel board, or a panel board in a plastic enclosure with EMT going into it.
I'm moving now to 314.4, metal boxes. Metal boxes containing circuits that operate over 350 volts or more must be connected to an equipment grounding conductor, and I think the reference I'd like to make on that would be 250.86. And also take a look at 250.48 because 250.86 says that metal boxes must be connected to the equipment grounding conductor. So that'd be a good reference on 314.4, maybe an author's comment we added in there.
Maybe get rid of the 50 volts thing because that's kind of...
Well, if it operates at 50 volts or more, because if it's less than 50 volts, then it doesn't have to be connected to the equipment grounding conductor because that's 250.112I.
Right.
Is that what that is?
It is.
Okay, good point,
It's a
yeah.
reference
Yeah.
to.
I just had to show this graphic of somebody adding extension rings. I had to use an excuse to use that graphic there.
Is one of them talking?
Let's go to 314.25, covers and canopies.
Yellow.
If you're putting a metal cover on a box, then you have to be sure that the metal faceplates must be connected to the equipment grounding conductor. And the only way you can do that I know of is going to have to be a metal box on with a metal cover plate. If you have a non-metallic box, then you cannot use a metal cover plate because you cannot connect the metal cover plate to the equipment grounding conductor. Handhold enclosures. Metal covers and exposed conductor surfaces of handhold enclosures containing branch circuits or feeder conductors must be connected to the equipment grounding conductor size in accordance with 251.22 based on the rating of the overcurrent device. We talked about this in the electrical fundamentals, how dangerous it is. If this is a utility, handhold cover, they will not have any overcurrent protection. And if there was a phase conductor to touch the cover, like happened on the service box in New York City with Jody Lane, it will energize the cover. We've had so many cases, people walking, kids getting off of school buses, it's raining, they take off the shoes, and they walk outside, and they touch these covers, and then they are killed. Don't go anywhere near handhold enclosures that have a metal cover, because they're required for our application to be bonded now to the equipment grounding conductor, but many of them are not. And this is an example of what a cover should look like. Here's your handhold enclosure, and here is a bonding strap that goes to that cover that makes sure that cover. Now, of course, we have to do what with the enclosure? Connect the enclosure to what? To the equipment grounding conductor.
An effective ground fault current path.
Exactly. Chapter 4, equipment for general use. Let's jump on switches, talking about snap switches. Your snap switches, including your dimmers, if it's mounted with metal screws to a metal box or a metal cover that's connected to an equipment grounding conductor in accordance with 250.148, well, those yokes are considered to be connected to an equipment grounding conductor. Because, see, the fear here is that you take a metal cover plate and you put it on a switch. And there could be a fault inside the box to the metal mounting yoke, and then the metal cover plate is energized. So the metal mounting yoke of the switch must be connected to an effective ground fault current path. And this is simply saying, if you get a metal box or metal plate, or if you take the receptacle and you connect it 251.48 of the receptacle to the cover, and the cover is connected with the flat crushed corners, with the receptacle connected to the cover with the locking mechanisms, well, then we're okay to do that. But the yoke has to be connected to the equipment grounding conductor. And then when you put on the plate, well, then the plate connected to the yoke would be considered connected to the equipment grounding conductor. If you have non-metallic boxes, then you can't connect the yoke to the cover and have it connected to equipment grounding conductor. It must have a circuit conductor inside, or rather brought to that particular mounting device and connected to that. That bonds the yoke in the event that you should put a metal cover plate to it. All right, let's take a look at the grounding and bonding requirements, actually really the bonding requirements in Article 406 receptacles. Well, this was covered in 250.146 that the grounding contactor receptacle had to be connected to the metal box, and we were going to show like maybe an equipment grounding conductor up here, right? Because that means that the box is connected. That's what I'm saying. We're going to add the word, a little acronym there, just so to remind us, okay, that's the equipment grounding conductor, which takes care of the box. So the grounding contacts connect to the box. We're good there. So here's what it reads. The grounding contacts receptacles must be connected to an equipment grounding conductor supplied with a branch circuit wiring in accordance with 251.46, which means bonded to the box. You don't have to have a wire directly to that receptacle. Now, if you have a two-wire receptacle that's existing and you want to replace it, you can replace it with another two-wire receptacle without a grounding contact. The other option is to replace a two-wire receptacle as per 406.4D2. Replace a two-wire receptacle with a grounding type receptacle, even if there's no equipment grounding conductor in the box. But when you do that, then you have to put a note on that receptacle, no equipment ground would be on that plate right there. Another option, take the two-wire receptacle, replace it with a GFCI type receptacle of the grounding type, and then the existing wiring that is feeding through, you could replace the two-wire receptacles here with grounding type receptacles without an equipment grounding conductor, but then you have to mark this receptacle right here as no equipment ground. Then you have to mark the downstream receptacles GFCI protected without an equipment ground. The other option is take the two-wire receptacles, replace them with three-wire receptacles, and the existing circuits downstream can be three-wire receptacles. If you had GFCI protection, like say at a circuit breaker to panel board, then I have to mark this receptacle here. This receptacle has to be marked, oh, here it is right here. Must be marked GFCI protected, no equipment ground on all of these receptacles. Ryan?
And if I could just mention briefly that this is the only time you need to put stickers on outlets. So if you're an inspector, stop making people put stickers on outlets unless you're replacing 2-wire. You know, I go and look at a $10 million house, and it's got stickers all over his kitchen. It's a brand new house.
Because it says GFCI, GFCI,
yeah,
GFCI.
GFCI on all the outlets. And
But does the instructions on the GFCI specifically say that you shall put these
not
stickers?
that I've seen.
Okay.
No.
Maybe somebody on the internet streaming, go find out. Do GFCI receptacles give instructions that specifically say you shall place this label on any receptacle that is GFCI protected downstream? If it doesn't say that, well, then it doesn't.
Yeah.
Now, GFCI, well, how, Mike, can you have a 2-wire receptacle without an equipment grounding conductor? How can you replace it with equipment grounding conductor type receptacles? And how does the GFCI operate without an equipment grounding conductor? Well, understand, GFCI operates with the imbalanced current between the phase and the neutral. That's all it's looking for. If current goes out on the phase conductor and the same current does not return on the neutral, and it's plus or minus 1 milliampere from 5 milliamperes, then it will sense the imbalance. It will tell the electronics to open up that circuit protection. Let's follow the logic. Current leaves, goes down to the phase conductor, goes to the load, returns back on the neutral. There's a 10 amp load right there. There's your 10 amps. However, current also takes a circuit down here. There's a ground fault, energizes the enclosure. Person makes contact, obviously pretty high impedance to get only 6 milliamperes. 6 milliamperes down at the knee, travels to the earth. Electrons are not going to ground. They are going to the source, travels up the grounded system, grounding electric conductor, gets back to the source. This sees the imbalance, and watch. This receptacle without an equipment grounding conductor, because it's GFCI protected, provides the protection for the person. And that's why the code permits that application. Now, back in 251.30c, which we did not talk about, if you take a 2-wire receptacle, you can replace it with a 3-wire receptacle, and then you can run an equipment grounding conductor just exposed, somewhat protected, but I mean, you can just kind of run it back to the grounding electrode system, or to the grounding electrode conductor, or to the panel board grounding terminal, or to an equipment grounding conductor of a different circuit if both circuits are connected to the same panel board, or take it back to the service neutral. Scott, you want to tell us about this rule?
Well, I was just going to say, when you look at this rule, you almost have a tendency to think, wow, did everything we cover, in these 2 DVDs mean nothing because you're letting me do this? I think it's kind of important to point out that this is a bad situation. It's existing 2-wire. You're never going to do this for a new install. It's never going to happen. And hopefully over time, all these 2-wire receptacles are just going to disappear. So it is something that just kind of, you only do this in somewhat of a disaster. Put a GFCI in here. Do something like that. That's going to be a lot better than doing this in some cases.
And I like what you're saying, and I want to pick up on that. I'm in an old house. I'm in a basement. This is a metal water piping system. Metal water piping system is being used as my grounding electrode. I have a receptacle right there, and there's my hot and my cold water. I replaced the 2-wire receptacle with a 3-wire type of receptacle, and I run an equipment grounding conductor right to the water pipe. That is a practical approach to that.
Right,
or
you're
I have
in a bad
panel
situation already.
Yeah,
so
or I
that's
have
a more practical application.
Or I'm in the basement and there's a panel there that has an equipment grounding conductor, but the old wire Romex didn't have an equipment grounding conductor in it, so I replaced the 2-wire receptacles with a 3-wire receptacle, run this wire over to the panel, and connected that equipment grounding terminal to the panel, and I'm okay. But you're saying maybe you should do both. Run the wire, but put it at GFCI. Might be a good idea.
Well, and let's be sure that we're making sense of this. We're not running it to the grounding electrode system because we want this thing stuck in the dirt. That grounding electrode water pipe is connected with a grounding electrode conductor to the service, to the utility neutral and effective ground fault current path. We're not doing this to just stick it on an electrode and call it a day.
Thank you. Yeah, because when I say go to the water pipe,
Yeah.
I was saying, and I meant grounding electrode, I might think, well, because that's connected to the neutral. You're saying,
Right.
Let's make sure we say that
Yeah,
so you
and
understand.
it's connected to the service.
It's service
Right.
neutral. That's what
Right.
we're talking about here, not to the grounding electrode.
Not the dirt.
All right, just something in 251.30c to be aware of, that you cannot make a branch circuit extension from an existing circuit that does not contain an equipment grounding conductor, unless the equipment grounding conductor is added back over to what we just discussed. So for all practical purposes, you're in an existing house and there's 2 wire receptacles. You can't come out of the box without an equipment grounding conductor and add on to that. You're going to have to do what? Go back to the panel board where there's an equipment grounding conductor and then start it from that location and then go on. You can't make extensions. Michael.
One of the mistakes people are making too with the no equipment ground using a GFCI is they plug in surge protection equipment that doesn't work. And a lot of the manufacturers won't warranty their plasma or flat string TVs unless it has the surge protection. The surge protection will not work without an equipment ground.
That's not true. I'm sure that's what they say.
No.
I'm saying, I'm sure that's
Well, if you have
what they-
MOVs to the equipment ground,
Without getting into detail, surge protection. Surge protection, when you're trying to protect your electronic equipment, you're looking to make sure you reduce the overvoltage to the equipment. The overvoltage is on your hot and neutral. Surge protection protects hot and neutral. It shunts the energy. It protects your equipment. The equipment grounding conductor is irrelevant to all of this. The reason people use the equipment grounding conductor for surge protection is because surge protection guys that provide surge protection properly, they don't have a connection to the equipment grounding conductor. Other guys provide surge protection, supposedly equipment grounding conductor. They say, well, we provide 9 modes of surge protection. Those guys only provide 6 modes of surge protection. So then everybody has to make sure that they put MOVs and surge protection going to the equipment grounding conductor so they can say we have surge protection that includes all the different possibilities. And then somebody thinks that the equipment grounding conductor somehow really has an effect on that, and they'll say, well, you need to have a low impedance ground for surge protection to operate, and without an equipment grounding conductor, surge protection doesn't operate, and then you hear it, and then you say it to me, you know what I mean? And in reality, it doesn't work that way. I've talked to people who design surge protection. You have this high voltage energy coming down. The hot and neutral conductor is going to get that equipment. You do what? You shunt it, you absorb the energy in the MOVs, and then you try to reduce the voltage. It's a little bit more involved. My point is this. If you have a 2-wire receptacle and you replace it with a 3-wire receptacle, you definitely want to get surge protection for your TV. The fact that the equipment grounding conductor is not there doesn't matter. You will get your performance. The TV guy might say it's not going to provide warranty, and the surge protection guy might say it might not provide warranty, and they can say whatever they want to say, but I'm encouraging you that when you want to protect your equipment, yes, you want to get surge protection for your equipment, whether or not there's an equipment grounding conductor there.
Mike, you asked the streamers about the GFCI rule on doing the labels, and Adam writes in, Pass and Seymour GFI instructions make no reference to utilization of the identification stickers.
All right, so we got a streamer telling us P&S does not say you have to take these stickers and put them on there, but they provide them in the information. I mean, it's there. Somebody might want to stick them on there.
Well, if you're replacing them, yeah, you have to have them. If you're using that for replacement
Oh,
of 2-wire.
Yeah,
you
yeah.
know,
But
so
you have to
yeah.
have the sticker, no equipment ground.
No
Yeah,
equipment
exactly.
ground.
Yeah,
GFCI protection.
comes with those stickers. Yeah.
All right, we're now in Article 450, transformers. There's really only one rule I want to specifically address, and it's covering the new chains, dry-type transformers, grounding and bonding, 450.10a. A terminal bar for grounding and bonding connections must be installed and bonded to the inside of the transformer enclosure. Now, I think 450.10a, doesn't it reference us something like 250. Another reference about cleaning off, was it 250.12?
Yes,
Okay,
12.
so it says, hey, listen, you got to comply with 250.12, which means that when you put this bonding, the equipment grounding bar inside the enclosure, you might have to take a grinder, grind off some of the paint. I don't like it. I don't like that stuff when you start grinding stuff and start doing stuff like that. But I guess I'd rather see the manufacturer put the grounding bus inside the enclosure and then it's taken care of. But either way, the code now requires it be a grounding bus, an equipment grounding, what is it called? Terminal bar. It requires a terminal bar that bar is going to have to comply with UL 467. That's a grounding and bonding bar, and it will have to terminate the equipment. You might have to put some screws and nuts and clean it up and what have you. So I like that rule. And let's take a look at this. This is my system bonding jumper. This is my supply side bonding jumper. This is the equipment grounding conductor coming from the primary side because it is a non-metallic raceway. Just showing the example that we have here. 517, healthcare facilities. 517.1, this is important to understand that Article 517 applies to electrical wiring in hospitals. nursing homes, limited care and supervisory care facilities, clinic and medical and dental offices, and ambulatory care facilities for humans. The reason they add the word for humans there is because it doesn't apply to a veterinarian facility having to do with non-human occupancy. 517.2 definitions, a couple we want to cover here. There's a definition now called a patient care space. It's a general definition. It's any space of a healthcare facility where patients are intended to be examined or treated. These spaces include basic, general, and critical care, as well as support spaces. Patient care space as the general care. That's an area where failure of equipment or a system is likely to cause minor injury to a patient or a caregiver, such as a chiropractor's office, a dentist's office, something like that. Now let's talk about 517.13, grounding of patient care areas. And here's a problem I have, guys, is that 517.2 changed the classification of a patient care area to a patient care space, but then 517.13 has the rules about patient care areas, and there is no definition of a patient care area in the code. So now we don't know what a patient care area is to apply 517.13. I'm going to go on the limb that patient care area of 517 is a mistake, and it's supposed to be a patient care space. Then we know what it is. So patient care spaces is what we did with our graphic, even though that's not technically what the code says, but we're going to go with that space. You have limited wire methods. Here's what it says. Branch circuit conductors serving patient care spaces must be contained in a metal raceway or a cable having a metal sheath that the sheath itself qualifies as an equipment grounding conductor in accordance with 250.118. And we talked about that. EMT, is that an equipment grounding conductor? Yes. Flex metal conduit up to 6 feet with circuits not exceeding 20 amperes? Yes. Type AC cable with the aluminum bonding strip, which what AC cable is, that sheath is an equipment grounding conductor? Yes. All-purpose metal clad cable, because it has a 10 gauge on a 12 gauge circuit here, it has a 10 gauge aluminum bonding strip. That cable is an equipment grounding conductor. Traditional MC cable, the outer sheath is not. Obviously, non-metallic raceways, the answer is no, it's not. So what can you use in a patient care space? EMT, flex up to 6 feet on a 20 ampere circuit or less, armor cable as much as you want to, or all-purpose MC cable. Now, let's take a look at 517.13a rules. The metal sheath of traditional MC cable isn't identified as an equipment grounding conductor. Therefore, this wire method is not permitted to be used for patient care spaces. Traditional MC cable, not happening. So what do you use? You use HCF, Healthcare Facility Cable. Ryan, did you want to say something about this one?
If you wouldn't mind going back one slide.
Okay.
You can buy MC cable with 2 green wires, and it still doesn't change the fact. You can, if they made MC cable with 100 green wires, it wouldn't change the fact.
Let me go back to this slide.
Yep.
Let's go with this graphic right here and talk about it right here now.
Okay, so yeah, you can buy MC cable that looks just like that, plus it has another green wire with a yellow stripe that we used to use for IGs. But that doesn't change anything.
Why can't I use MC cable with 2 ground wires or PVC with 2 ground wires?
And this is the reason I hate that term, redundant ground. This is the rule. You have to have a metal pipe.
Right. The reason is because the rule says that the raceway or the sheath of the cable has to qualify as an equipment grounding conductor. And because this sheath of this cable does not qualify as an equipment grounding conductor,
it's out.
And it doesn't really matter.
Yep.
Because, see, 517.13a is requiring an equipment grounding conductor of the mechanical type, a mechanical equipment grounding conductor. You can't put 2 equipment grounding conductors of the wire type to make one that's a mechanical ground. So you need a mechanical equipment grounding conductor. Then 517.13b talks about a wire type equipment grounding conductor, and we're having 2 different types of equipment grounding conductors, the mechanical type and the wire type, not PVC with 2 equipment grounding conductors, not MC cable with 2 equipment grounding conductors. They have to be 2 different types of equipment grounding conductors, one mechanical, one of the wire type. 517.13a, mechanical, 517.13b of the wire type. Scott?
Yeah, what I was going to say is one place where a lot of folks get in trouble, and that's a dentist office and a dentist chair. They run the
that's
PVC
exactly right.
and the slab. And all of a sudden, because they get used to that. Oh, it's a slab. I got to run PVC. Then, oh, I'll just put 2 green wires in it.
All right,
No,
let me review
not
that
gonna
again. In patient care spaces, all the branch circuit wiring to this equipment has to be installed in a wire method that meets 517.13a requirements. PVC does not meet it. So therefore, if you have a dental office, and I know I've done dental offices, you do not slab the dental chair in PVC because it doesn't meet 517.13a requirements.
No exception.
Unless you made a large enough raceway and you pulled MC cable and it wasn't on the ground floor slab and it wasn't a wet location, right? And then you use
Yeah, just
MC
don't go
cable
there.
that the outer sheath is listed as an equipment grounding. In other words, you'd have to have the law of compensating errors. You have to make so many mistakes that you actually got it right. All right, we're off.
Yeah.
We're going to
Use rigid metal conduit. There you go.
Yeah, there you
Put
go.
rigid.
Rigid
put-
or IMC? Underground.
1 second. Can't I slab? No, MC cable.
No.
No,
No,
I can't.
no.
I can slab MC cable, but it's not listed as equipment grounding conductor. So therefore, I can't do it.
Right.
All right, let's go back to it. 517.13a, MC cable, not happening. 517.13a, another example. Armor cable, yes, we're okay because that's listed at equipment grounding conductor. MC cable, all purpose, yes, because that's listed as an equipment grounding conductor, which is the outer sheath, and then we'll meet the equipment grounding conductor of 517.13b a little later on. 517.13b1 says, the grounding contacts of receptacles must be connected to an insulated copper equipment grounding conductor. So now, you bring equipment grounding conductors in the box, you connect it to the box in 250.146 from the, well, actually 148. We talk about bonding the box. Then the grounding contacts of receptacle must connect it to the equipment grounding conductor. That's 250.146, I think is A on that one. We're good. Metal enclosures, this is 517.13b12. Metal enclosures containing receptacles must be connected to an insulated equipment grounding conductor. Now, this one requires me to bring an equipment grounding conductor in the wire method and connect it to the box. 517.13b13 says fixed metal parts of fixed electric equipment operating at over 100 volts must be connected to an insulated equipment grounding conductor. So now that means I have to bring an equipment grounding conductor to all metal parts. That means a switch. One had to go to the box. Now you have to go to the switch. One has to go to the box. Now one's going to have to go to the equipment. You have to bring an insulated equipment grounding conductor to all of the electrical equipment. 517.13b13 exception, faceplates can be connected to the equipment grounding conductor by the metal mounting screws. So I bring an equipment grounding conductor connected to the box. That equipment grounding conductor goes to the switch. The switch is connected to the equipment grounding conductor. I put a metal cover plate with the screws that are metal, does it say metal screws in here? Metal mounting screws, and therefore this metal cover plate is bonded to the yoke. The yoke is connected to the equipment grounding conductor, which is provided with the mechanical connection of that wire method that's listed as an equipment grounding conductor. Okay, patient care space, luminaires connected to the equipment grounding conductor. This is 517.13b13 exception 2. Okay, before we actually take a look at this, we have to understand something. We are in 517.13b. This is talking about that you have to have an equipment grounding conductor of the wire type. It has to be insulated, no smaller than 12-gauge wire. You're going to size it based upon 250.122. You're going to take it to the box. You're going to take it to the switch. You're going to take it to the receptacle. You're going to take it to the equipment. So that's in B. This exception in B has to do with the insulated copper equipment grounding conductor, which means you don't have to have that. So understand the context. 517.13a still applies that you need an equipment grounding conductor of the wiring method type, of the raceway type, of the enclosure type, of the mechanical type. So we're not losing that. So let's make sure we read this exception clearly. Let's look at it. Luminaires more than 7.5 feet above the floor are going to be required to be connected to the equipment ground return path complying with 517.13a. However, they do not need to be connected with an insulated copper equipment grounding conductor. So now let's think about this. I'm going to have to run to the luminaires, EMT. Flex, not more than 6 feet. Armor, AC cable, armor cable, that's okay because it has the bonding strip. I cannot use traditional MC cable because it doesn't comply with 517.13a. Then I have to use the MC all-purpose cable. And I'm thinking, man, you're not really giving me much an exception here because I still have to have the same wiring methods. I just don't have to have a copper insulated minimum 12 gauge. I think it's minimum 12 gauge. Is that right? And check and verify that it's a minimum 12 gauge of 517.13b because I thought it said minimum 12 gauge. Maybe it just simply says size in accordance with 250.122. So I don't see this exception really helping you anything. Nothing in there about the 12 gauge on 517.13b? Okay, so just size and 250.122. Ryan?
The other wiring method you can use for luminaires, and this comes up very often, is if it comes with the whip, right? That's not MC cable. You know, as far as like a 2 foot by 4 foot troffer, comes with a whip. That's not an MC cable. That's 3/8 flexible metal conduit, less than 6 feet long. You know, vibration, all that jazz. So you can use that.
Okay, so it allows you to use the fixture whips is what it's doing. Basically, this is an exception, not for the wiring methods most guys are using. This is that when you buy the lay-in fixtures and it has the whip that's an equipment ground, that's flexible metal conduit.
Yep.
Without an equipment grounding conductor, we're good to go.
Yes.
So that's where I can see that. We probably need to make that graphic better. Would be a graphic to use for this application. This is talking about on 517.13b2 on the sizing of the equipment grounding conductor. And it's sized based on 250.122. I mentioned a couple of times here about no smaller than 12 gauge, and I guess maybe a few cycles ago, maybe it said no smaller than 12 gauge. That's not the code. It's just simply, what size overcurrent device?
Yep.
250.122? That size equipment grounding conductor. Okay, Article 547, agricultural buildings. It's important to understand the scope of 547. It applies to buildings or areas where excessive dust or dust with water may accumulate, such as areas of poultry, livestock, and fish confinement systems where litter or feed may accumulate. Now, the state of Washington and Washington Administrative Code specifically says that it does not apply to non-commercial agricultural buildings. Okay, so that's interesting. So some local codes will identify, well, when do you have an agricultural building? So Washington State and the Administrative Code actually says, well, if it's residential, then it's not an agricultural building. But other ones. But the code doesn't identify it that close. Let's talk about what the requirements are. There's a definition that was revised in 547.2 relating to equal potential plane. An area where conductive elements are embedded in or placed under concrete and bonded to the electrical system to minimize voltage differences within the plane. Now, I don't have the time for sure in this class to explain stray voltage. Stray voltage is also called neutral to earth voltage. Go to mycolt.com, go to video, and I think it's about 2 hours or 2 hours and 15 minutes that really gets into all of the details as it relates to equal potential plane, stray voltage, neutral earth voltage. So if you are dealing with agricultural buildings and you have a scenario where you have in Wyoming where they have a water trough and the animals won't drink out of the water trough, you're in a dairy farm where there's what's it called, mastitis? What do they call that? The stomach
Mastitis.
Mastitis, where
they won't
and
produce
of course
milk.
the bacteria count starts going up, and then there's lots of problems dealing with dairy issues. Go to mycolt.com, go to videos, and we'll see if we can fit this on the DVD. Probably it's not going to be any room as a bonus, but if we can, maybe we'll pick up a third DVD on the grounding and bonding to get that information. So just wanted to whet your appetite on 547, let you know the resources we have to get you on to the next level. Okay, let's go on to the next section. Chapter 6, Special Equipment. 680, pool, spas, hot tubs, and similar installations. Permanently installed outdoor spas and hot tub installations. We're going to go to 680.21, pool-associated motors. The rule here in 680.21 is when you get into swimming pools and you're hooking up a motor, there are specific wiring methods that you can limit it to be used. If you take a look at this application right here, you can use liquid type for a motor, rigid metal conduit, maybe coming into that motor circuit, intermediate metal conduit, PVC, and MC cable listed for the location, maybe like for direct burial, as well as EMT in or on a building. The caution I want you to understand is if you're an electrical contractor, I would strongly recommend you do not do swimming pools. I don't know anybody who does swimming pools who makes money unless you are an expert at swimming pools. And that's all you do. You spend all the time in swimming pools. Because if you're going to get into swimming pools, you might as well wire up hospitals. You might as well do hazardous classified locations. Those are 3 areas that you don't dabble in. You don't try to get into. You decide, I'm going to be the pool guy. I'm going to learn everything there is about swimming pools because it is so complicated, 680, with part 1, part 2, and part 3. Part 1, part 3 is you use part 1, and part 4 you use part 2 and 3. And then, of course, you got all these special wiring methods and all the special applications. It is extremely complicated. There's restricted wiring methods, like healthcare facilities. You have restricted methods to do that. So be very, very, very careful when you get into swimming pools. That would be my strongest thing in the beginning. So when you run a circuit to a motor, you don't just simply run the way you think it is. There might be restriction. Let's take a look at 680.21A4. When you're dealing with a one-family dwelling, as the title says there, any Chapter 3 wiring method for the interior of a dwelling unit can be used for a pool-associated motor. So when it gets to dwelling units, they kind of give you a little bit free rein there. Feeder wiring methods, 680.25. The feeder conductors, let's say to this panel right here. Here's a feeder coming into this panel right here. You have limited wiring methods for the feeders. You can use, let's see what we got here. Must be rigid or IMC. If not subject to physical damage, you can use liquid-tight, flexible, non-metallic conduit, PVC wiring methods, electrical metallic tubing in or on a building, electrical non-metallic tubing were installed within a building, type MC cable within a building and not subject to corrosion can be used. So you got to be real careful that when you're running a circuit to a feeder that you understand that there's limited wiring methods. Now, guys, do me a favor. Help me here on 680.25. I did not, I don't have a graphic showing this, but don't I have to have an equipment grounding conductor in these specific wiring methods for the feeder going out to the motor? And I think it's 680.25 telling me that you're going to have an insulated copper equipment. What rule is that, Ryan?
680.25B.
Okay, I don't have the graphic in there. We probably need to add a graphic in there.
Yeah.
The 680.25B. Could you read it for me?
Certainly. An equipment grounding conductor must be installed with the feeder conductors between the grounding terminal of the pool equipment panel board and the grounding terminal of the applicable service equipment or source of a separately derived system. For other than 1, existing feeders covered in A exception, or 2, feeders to separate buildings that don't have an insulated equipment grounding conductor. Other than those 2, the equipment grounding conductor has to be insulated.
So you can't run SER cable.
See, and that's there's an exception for, and this was changed in the 2014. So I gotta kind of set this up. In 2011, it said for existing installations, you could have a bare conductor for feeder applications in a dwelling. They changed that in 2014, and I think they broke it. They removed the thing about existing installations, so it could be for new installations now, which is great. The problem is it has to be insulated now. So SE cable's gone.
Right.
SER cable, and that was that was what we needed. That's the exception was necessary for SER cable. So
what I'm saying is,
Yeah.
you cannot run SER cable.
That's correct.
From a residential panel out to another panel, let's say on the other side of the house.
Yeah.
So you can pick up the feeder for pool equipment.
exactly.
You're going to have to run PVC. This is what I'm trying to say. You got to be careful. You're going to do swimming pools. You're going to need to start from the beginning of Article 680. We'll be covering this in our DVD that we'll be doing sometime in probably March or April. We'll have a DVD on that, and we're going to get really into swimming pools and all those details. So please, just be careful about that. Moving on, 680.26. Equal potential bonding is intended to reduce voltage gradients. Okay, swimming pools. Stray voltage, also called neutral earth voltage. Really, really complicated topic beyond the scope of this particular class. But we have MikeHolt.com. There's a link on videos. There is a link there on stray voltage. Watch that, because that whole thing ties in with agricultural buildings and swimming pools. And what are we trying to accomplish and why are we trying to accomplish it? It's not the scope of this, but that's not the fundamentals of this program right here. I'm just going to cover what does the code tell you you're supposed to do. So let's take a look at the rules here, okay? Here you go. Here's a voltmeter. You touch the metal enclosure, you go to concrete, and you measure 2.88 volts. That is not a good thing. What it should measure is how many volts, guys? Approximately what?
Zero.
Zero. That means that somehow, because this has stray voltage on it, I should have this concrete right here have the same amount of voltage, and we'd have then an equal potential bonding performance here. So here's what the code says. Metal parts of pool structures must be bonded together with a solid copper conductor not smaller than 8 gauge. Mike, why does it have to be solid? Well, because you're in corrosive environments. You don't want to use a stranded conductor to be bonding all these parts together. The goal here is this. The electrical system is going to have an elevated voltage because the electrical system is connected to the utility primary neutral. That's just the way it works. And when you have an elevated voltage on the equipment grounding conductor, because the equipment grounding conductor of electrical premises are connected to the utility primary neutral is elevated at that point relative to its system where it started at the substation. All the metal parts in a building is going to be at elevated voltage. Now, on the normal conditions, we don't notice this. But when you start elevating something 1, 2, 3, 4, 5, 6, 7, 8 volts, relative to something else, and you're in water and you're in bare feet, you're in the water itself, you're stepping out of the water, you will easily notice probably about 1 volt or more. And it can be very disconcerting when a woman is in the water, she has children, she's in the water, she feels a tingle, she feels a shock. A guy's like, no big deal. Guys, we're idiots, right? We're like, it's fine, it's not going to kill you. Where a woman is like, whoa, wait a minute now. This is not right. And so the goal here is to make sure we bond everything together so that everything has the same potential, so that 1, 2, 3, or 5 volts, we don't notice a difference between the two. That's the major part. This is a little bit more involved than that, having to do with utility losing a neutral and other fault conditions. But if we can get the basics, then we have the same thing. So take a look here. So we have to bond all these things together with a solid 8-gauge copper conductor. Now, what do you bond together? Well, 68026B says bond all these things together. Ready? Unencapsulated structural reinforcing steel in a concrete secured together by steel tie wires. So if you have a concrete gunite pool and you have steel inside there and it's unencapsulated structural, then that is important. Now, here's what happens. You have a concrete pool, you have steel that's unencapsulated. You're going to bond that to the pump motor. Now, the pump motor, let me just pick a number, 2.88 volts. Okay, that's the stray voltage value. That's the NEV, neutral to earth value. Now, the motor is 2.88 volts. I take a wire from the motor and I bring it to the structural steel of the pool, the rebar. Now, the rebar is what? 2.88 volts. You're standing inside the pool, and since you're on the concrete in the rebar of the concrete pool, you are standing on 2.88 volts. So far, we've bonded those two. The water now has the same potential as the concrete. The concrete has the same potential as the motor there. I know of a case where people have gotten shocked. Oh, by the way, you're in the water, put your hands on the deck. Let's say the deck is not an equal potential bonding at all. Well, if the deck is not equal potential bonding, the perimeter around that deck, that means the deck is going to have 0 volts. You're standing on what? 2.88. When you put your hand on the deck, you're going to notice what? You're going to notice the voltage. You're going to notice every little cut and crack that you have in your entire body, you will notice that voltage. Now you're going to start to freak out. And that happened in California. They built 2 brand new pools for over $1 million. You know what they use? They use epoxy-coated rebar. Once you use epoxy-coated rebar, then guess what? The water had the voltage of 0. You were standing on 0, but if the deck was properly bonded, the deck would have had what? 2.88 volts. And then when you start touching the handrails. So there's nothing you can do about that pool at all. You're going to have to remove the pool. Ryan?
Did you say if the deck was or was not
If the
properly?
deck was properly bonded,
Okay.
then the deck now is 2.88 volts.
Yes.
But you're standing on 0 volts, and now you're getting shocked again. So when they found out there was a problem with the voltage, people were getting shocked. They weren't sure quite what it was, and then they found out it was epoxy-coated rebar. You can't fix that. You're like, you can't fix stupid, right? I mean, the same thing here. I mean, you can't fix that. They had to take the entire, close it down, take the entire pool out, put it back in again, and do what? Put conductive rebar, make it 2.88, have the deck 2.88, have the motor connected to that, and then there's no difference in potential. So that's number one. Number two is the equipotential bond must extend 3 feet beyond the inside wall of the pool for the purposes we described. This is an example of what it would look like. Now, the code does not tell you how to create this equipotential bond around the perimeter pool. How far do you, what size rebar, how far you separate it. I mean, there's nothing specific. Here's an example of somebody, I think he took maybe like an art class or something like that, and how he ran that rebar in like the, I mean, like, who would do something like this? But guess what? The code doesn't tell you that's right. It doesn't tell you that's wrong, as long as you are within what? Now, did we have to be this far away? No. We only had to be what? Just 3 feet around. Now, you have metal here. We want to do what? Do we want an equal potential bond around that? Yes. We want to make sure no matter what you touch, look, we want this to be what? 2.88 volts. We want this rebar to be what? 2.88 volts. We want this handrail going into the water, both of those, because they're both metallic, 2.88. We want this metal part for this diving platform to be what? 2.88. We want the metal slide. We want it to be what? We want, no matter what you touch here, and you're in the water, we want the rebar. By the way, this is a vinyl pool. So we got to make sure that we energize the water. We do that by doing what? Bonding this ladder that goes in there, bond that to the rebar, have the rebar bonded to the motor. I've now energized the voltage in the water. The water's 2.88. I'm in good shape. Ryan?
And just so we're clear, we're just throwing 2.88 out there. We want to make sure all these things are the same voltage.
Yes.
Whether that's 2.88 or under some weird, extravagant circumstance, maybe it's all 1,000. Whatever it is, though,
and it could
the
be.
same.
It could be.
You know?
And the only reason I'm using 2.8 only
Right.
because I'm saying if we were using this example, and if this were the
Right.
case, and the voltmeter was 2.88, and by the way, let me make a comment about that. The voltmeter that you're measuring is NEV voltage. It will be changing during the daytime. You'll start at 2.88, and by the time you get done with a couple hours, it's now 3.1, 3.4, 3.6. It has to do with the loading of the utility primary neutral conductor. 4 o'clock in the morning, 5 o'clock in the morning, maybe it's 1.6 volts, and then as it goes up and it goes down, during the summertime, the wintertime, air conditioning loads, heating loads, what's going to be taking place? So using that example that if it were 2.88 and it didn't change during the day while we're working that, that's what we're working with these volts, just a sample that we're working from. Now, if you don't do a creative perimeter bonding grid like this, then you can just simply take a copper conductor, 8-gauge solid, bare, and go 18 to 24 inches from the edge of the water around that perimeter. And that would be another alternate method instead of using the rebar. Now, bonding parts. Metal parts of the pool structure must be bonded to the equal bonding grid. And that would be like, I can't think of any particular parts in there. But B5 talks about metal fittings. Metal fittings 4 inches and larger within or attached to the pool structure, such as ladders and handrails, are going to have to be bonded. There's a little cup right here where this slides in, and it has a screw on there that you bond that right back over to all these different parts. You're bonding everything together and ultimately going to the motor. Michael.
Mike, back on that other slide, even if you don't have concrete around the pool, you just mentioned concrete. If it's just dirt, you still have to put that 18 to 24 perimeter bond.
You know, I was hoping nobody would say something. I was really hoping
Sorry
nobody
about
would
that.
go
Even
there.
if it's wood.
Okay, let's cover what it says. It says you have to have the perimeter bonded 3 feet around. Thank you, Michael, for bringing this.
You're welcome.
So if you choose to put a wood deck around your pool, and this was an elevated pool,
Yeah.
you have to nail either rebar underneath your wood deck,
Right.
or probably the easiest way is to take a copper 8-gauge conductor, solid, and nail it to the bottom of your wood deck, because you have to have an equal potential grid along the perimeter. So take a look at the language there. No matter what you do, no matter the fact that you're not standing on the earth, it doesn't really matter at all. So back to your point that you said, is that if you have no pavers, you have no concrete, you need to have an equal potential bonding grid around that. And maybe the easiest way is to run, I don't even give you a burial depth on here, Is it 6 inches down? Does it say anything about that on the 26B, 2B?
4 to
4 to
6.
6.
Okay, I thought it said. So you have to put
Pretty
it in the
precise
dirt.
there.
4 to 6 inches
Yeah.
in the dirt. Which I agree with the dirt part.
Yeah.
Because you're in the pool, you're at 2.88 imaginary example, and you put your hand on the grass, you know, so there are these, but I mean, if it's a wood deck, well, it's insulated, but code
Very
says
few
it.
people pour the concrete the first year, they let it settle. So we still have to have that there. I mean, they're utilizing the pool for a whole year without the concrete,
You're right.
and they pour it later.
That's a good
Ryan?
point. Yeah, you know, when I'm in the field, I don't recommend things very often. I'm there to enforce things, and I don't give people my feelings and whatnot. But I always tell people, use the one piece of 8-gauge metal around the pool when we're pouring concrete, because at least the code tells you exactly what you have to do. Put it 18 to 24, follow the contour of the pool, and then pour concrete on it, you're done. Don't get in arguments with the inspector, because one inspector is going to say, oh, the rebar's got to be 2 feet by 2 feet, and the next guy is going to say it's got to be 12 by 12, and no matter
You
what.
got to have
know,
a 5/8
you got to
inch,
flip a
half
coin,
inch.
and yep. Look,
Yeah,
the code
that's-
says, you know, prescriptively run one number 8. That's your best bet, I think.
I like that. All right, so now we talked about handrails and larger fittings that are going to be in the pool. You bond that. Number 6, metal parts of electrical equipment associated with the water circulating. That would be heaters, electrical equipment with electrical heaters and pump motors. So you can see, here's a pool heater, electrical. That's bonded. Motor, bonded. You have a metal diving platform. That's bonded. The rebar is all, of course, bonded together. You have a wet niche lighting fixture. The metal wet niche is bonded. You have the rebar inside the pool. You can use the rebar of the pool to bond the handrail, but you got to bond both ends of that. Let's make sure this is a non-metallic steps here, which is traditional. Then we want to put a bond on both ends of that. And that takes care of this part up to 6. 7, this is nuts. Fixed metal parts, including but not limited to metal sheath cables and raceways, metal piping, metal awnings, metal fences, metal doors, and metal window frames. When I came out that in the 2011 code, I'm like, this is the poster child of 2011 of the most ridiculous rule. And the poster child of 2014 is the solar voltaic rule on auxiliary electrodes on 690.4070. These are like the are you kidding me rules. Here's an actual photo. You can't really see that. There's an actual photo of a roof flashing with the bonding conductor actually going up to it. There are people actually making contractors run a wire, and guess what? Understand something here. We didn't get into how straight voltage works, but the metal flashing on the roof has no voltage, right? Has no voltage to begin with. As soon as you connect voltage on there, I know of a guy that was doing a satellite, and something happened that he touched something, and he touched the metal flashing, and he almost fell off because the metal flashing now is connected to what? To the electrical system. So here people are, the same thing happens to a window. You take a window that has no conductive path to the electrical source. It's like having non-metallic plumbing piping with all non-metallic, and then having metal parts, and then doing what? Going around and running a wire from a dangerous electrical system to energize all the metal piping inside the building. You're going to energize the sliding glass doors so people can get killed inside. You're going to energize the window frames, the awnings, the roof flashings. Wait a minute now. You need to go to MikeHolt.com. You need to learn about straight voltage, and you need to make some proposals in the 2017 code. This is nuts. Back to where, but this is what the code says. You have to bond the window frames. You have to bond how do you bond it? I mean, you can't use sheet metal screws. You can't use wood screws anymore like we could a few code cycles ago. Do you have to make 2 threads engaged, and do I have to go to 250.8? I mean, I've done this once before. I actually drilled a hole in a sliding glass door because I wanted to put in a pin, and guess what happened? My whole sliding glass door. I'm like, crap. Man, I should have called somebody to do that. I can see sliding glass doors. In Florida, you have sliding glass doors, which is all tempered. And when you go on the top and you just hit with a little drill bit, a little tiny point, the whole thing shatters. So now how are you going to get a sliding glass, the door frames and the window frames? Michael.
Not the glass.
I don't usually give advice, but like Ryan, I tell him, maybe you want to put that fence 5.5 feet from the edge of the pool.
Because the rule here, that bonding doesn't apply where it's separated by a barrier. This bonding doesn't apply if it's more than 5 feet, and the bonding doesn't apply if it's more than 12 feet vertically. All right. Now, revision of this rule that came in 11, that revised in 14, is that the water has to be bonded. If the water does not have electrical connections to one of the bonding parts described in 26B, if you don't have a ladder in there, if you don't have a pool light in there, if you don't have a handrail making contact with the water, then the water has no potential. Then what we need to do is we need to make sure that you have the water have the same potential by an approved corrosion-resistant conductive surface that's at least 9 square inches, and it's located in the water, and I don't think we have it in the text here, but it's located so it can't be damaged. And what they do is they have skimmers. They have these devices. The guys come out with a device. He's contacted me. You put it in the skimmer, then you kind of bolt it in there, and then underneath the pool, behind the skimmer, is your lug, and then you connect that to it. So therefore, in these fiberglass pools or vinyl pools, you're able to bond it. If there's no pool light, if there's no handrail, if there's no ladder, in other words, there's no other metal part that was bonded in 250-26B that's already in the water, then you have to bond the water. Why? Watch what happens. If you don't bond the water and somebody drops a 2-wire cord into the swimming pool, then you cannot trip a GFCI because current leaves the phase conductor, it returns back on the neutral conductor, it creates a voltage gradient in the water, and it will not trip the GFCI. But what happens if you're in a vinyl pool and you have a 2-wire cord in there and you put your hand on the deck? Will it then trip?
Interesting.
I'm in the pool.
Blow it up, Connie.
If you do it before you die, you mean?
If you can do it
Or is this
before you
as
die.
a corpse? Okay.
If you do it before you die, you're in the water. It's 120 volts.
Yes. If it pulls more than 4 to 6 milliamps of current through you and back to the source, then my answer would be yes.
Let me show you a videotape.
Yeah.
This is a video by Joe Tedesco. Joe has a tendency to come up with some very interesting videos. And I guess he did this in a hotel we're staying in. He has a hairdryer in the water that is plugged into a GFCI protected receptacle.
Right. Well, it's not bonded back. There's no other path back, so it's just in out
It's a
the line.
2-wire
back to neutral.
attachment cord.
Right. Sure.
And the reason it doesn't trip is why? Current is
trip
coming into the water.
Right. It's going
It's
right back
returning
out.
back on the water through the GFCI. The GFCI does not sense it to be a fault condition. But in that particular case, if somebody had done what? If somebody had put their hands in the water and stood on the earth, then in that particular case, they would have ended up tripping
Yes.
the GFCI, right?
Absolutely.
But
well,
That won't work in a vinyl pool.
Well-
But in a vinyl pool, if you're in the water,
Right.
you have the voltage gradient.
See, that's the
if
thing.
you could, now we don't know how the voltage gradient works.
That's the
We don't
key.
know how close you are to it. If you're far enough away from it, is that right? And you're not getting wrapped around as the water, all the parallel paths knocking you out, because it doesn't take many volts to do that. And you touch the deck, now current comes in, goes back on the neutral, but comes in, travels your hands, and if you get 5 milliamps plus or minus 1, it trips the GFCI. But the thing is, we don't want that. What do we want? We want the
want
water
to
to
trip.
be bonded, so if you drop a 2-wire cord, boom, the GFCI trips instantly. Yes, Scott.
Well, what I was going to say is, you mentioned it earlier. I think it really bears repeating, and what you said is what we do in our company. We don't do pools. I mean, now we're under contract that involve pools. We do hotels, things of that nature. That portion of the job, we subcontract to guys who do pools. I mean, there's just no way. I mean, I know a little bit about grounding and bonding, to say the least, but you know what? Swimming pools is a whole nother world. There's a lot of other subtleties that go with it, not just grounding and bonding. It's really important to not get yourself in trouble. Just find the pool guys. They're around. They know how to do it. That's great advice, Mike. Great advice.
Ryan?
the pool water thing I was having really trouble with. I don't do a lot of pools. I live in Salt Lake City. In fact, my wife just sent me a text. We're getting pounded with snow right now. We don't have swimming pools, right? But I had to inspect a vinyl pool a couple of months ago, and I'd had this pool water bonding thing come up, and the guy was freaked because he'd never heard of it, and he doesn't know what to do. And I told him there's plates and scuppers and things, and he brought in his niche, his wet niche,
Right.
and showed it to me, which of course is bonded. And I didn't know this, maybe I'm the last person on earth to not know this, but the wet niche, you put the luminaire in, that water is going through the niche at all times. The light is submerged in water, and that would give you the 9 square inches you need. So if you had a wet niche luminaire, you're set.
Exactly right. That's one of the bonding means in
Yeah,
250.26b.
Right.
You have that
I
there.
didn't realize that the water actually touched the niche. I thought it was sealed and, you know.
Gotcha. All right, we're moving now to part 4, spas and hot tubs. Now, this is a change made. This was a TIA, a tentative interim amendment between the 2011 and 2014 code. And then the 2014 code added the rule. It says equal potential bonding of the perimeter surface is not required for listed self-contained spas for above ground use. In other words, you go to a store and they sell these spas and people buy them and they come out to drop it off and they hardwire this thing to a disconnect that has to be no closer than 5 feet and everything is fine. But then all of a sudden some inspectors say, well, wait a minute now. You need a 3-foot perimeter bond all around that, and all of a sudden now the guy has a major problem that he sold the spa to because now they